Welcome to the project of building an electric, four-wheeled off-road vehicle with deep engineering. The project kicks off with two electric, direct-drive hub motors offering excellent traction. The engineer carefully installs retaining washers onto the stator shaft to reduce mechanical shock. A carbon steel bolt clamped on a wooden block is precisely ground down to the exact thickness using a grinder. The builder uses an angle square and a marker to draw precise lines on a rectangular steel box billet. The cutting blade makes decisive grooves to form a U-shaped mounting bracket with excellent bending resistance. Locking pliers firmly secure the U-shaped billet on the machine table to drill and tap a perfectly concentric hole. Next, a perfectly fitting cylindrical galvanized pipe is also machined with a cross-drilled hole, using TIG welding technology to connect a threaded shaft into the round cylindrical pipe body, assembling them with an axle bolt to create an extremely flexible mechanical oscillating hinge joint. Two thick-walled load-bearing steel pipe billets are chamfered at calculated angles, positioned and butt-welded into a V shape to form the front suspension A-arm structure. TIG welding securely locks the apex of the V-angle and welds the U-shaped hinges to both ends. A triangular steel gusset plate is weld reinforced to completely eliminate torsional deformation forces. A caliper measures to determine the motor's threaded shaft aperture, and the data is applied onto a solid steel flat bar billet, marking the center, drawing lines, drilling pilot holes, and sketching the exact profile of the axle retaining dropout. Meticulous hand cutting with an angle grinder creates perfect dropout sliding slots, continuing to cut and shape the thickness of the flat steel billet to create the mounting base for the rear motor assembly. The rear axle subframe is welded as a single solid block into a rigid rectangular shape with cross braces. The dropouts are perfectly aligned coplanar, facing one direction to receive the motor axles. The engineer proceeds to sequentially install the two rear wheel motor assemblies, sliding them into the rectangular base dropouts, tightening the lock nuts with a wrench to prevent axle rotation reaction force when the motor generates torque. The two front wheel motor assemblies are attached directly to the A-arms via the hinges. The system is now separated into two distinct modules, a fixed rear axle assembly and an independent suspension system. The builder uses a measuring tape to measure and cut off a section of square steel box tubing to make a cross brace, a stepping stone in preparation to connect the suspension module in the front to the rear motor base chassis. Welding the square steel box tubing directly the front suspension module and the rear drive motor assembly. A tape measure checks the wheelbase length to ensure a perfect weight distribution ratio. A thick steel pipe is fed into a mechanical bending machine using the principle of pulleys and leverage. The engineer bends the billet into a beautiful U shape. This will be the main load-bearing chassis frame, supporting the entire saddle and the rider. The builder marks the center to drill through two symmetrical holes on the two branches of the U-shaped steel frame, using an angle square to draw lines and scale proportions precisely on a thick, load-bearing flat steel billet, drawing a curved profile arc in preparation for the cutting and grinding process. The builder inserts bolts through the drilled holes, securely locking two small steel brackets along both sides of the U-shaped frame, preparing a short cylindrical steel billet and a high-intensity center load-bearing roller bearing, using a mechanical vise to tightly press the bearing into the steel pipe. Arc welding technology is used again to connect a horizontal shaft, forming a solid T-joint. This steering pivot assembly is inserted into the head of the U-shaped frame. It acts as the core central rotation axis for the vehicle's entire steering system. Welding fixed a round flange with pre-installed bolts to act as a steering gearbox mount beneath the pivot mechanism. The steel handlebar is also bent, shaping the ergonomic posture for the rider. Test fitting the handlebar onto the steering stem to check the rotation angle. Moving on to drill and machine. 4 positioning holes around the edge of a thin, solid carbon steel round disc billet, cutting 2 additional large holes using an alloy hole saw to optimize and minimize unnecessary weight. Then cutting the round disc in half into 2 semicircles, welding a bearing into each half moon piece, creating 2 highly independent steering swivel mounts, assembling them onto a mechanical threaded shaft assembly, with a metal centering bushing right in the middle. This is an ultra-complex multi-steering mechanism. Tack welding this central steering assembly to the cross brace, bearing the lateral load of the front suspension base. Fabricating 2 steering tie rods to transfer direct drive. 2. The U-brackets on the wheel axles, locking with nuts to complete the multi-point tie rod mechanism. The engineer prepares 2 coilover shock absorbers, with hydraulic damping specialized for off-road use. Install the U-shaped steel brackets using through bolts through the mounting eyelets on both ends of the shock absorber. This system will completely absorb any vibrations. Assemble the massive pivot joint with integrated bearings, connecting the front suspension mount to the rear chassis. This dynamic mechanical joint allows the 2 halves of the vehicle to twist independently while driving. Position the shock absorber in the center for butt welding, connecting the front and rear suspension modules via the shock absorber pivot points. Continue welding to secure the mounting base for the pair of shock absorbers onto the A-arm structure of the front frame. The engineer uses their body weight to bounce on it, testing the suspension travel. Next, connect the steering tie rod brackets to the front wheel hubs using high tensile bolts. A close-up of the steering mechanism reveals the complexity of the multi-point tie rod system. The U-shaped steel frame is moved into position and welded securely to the central pivot. The tail of the U-frame is connected to the top of the rear shocks, providing a solid base for the seat. The ergonomic leather seat is placed on top and secured with screws drilled through the U-frame. A practical test verifies the leaning mechanism, allowing the cockpit to tilt independently while maintaining maximum traction on all 4 wheels. Moving on to the power supply phase, the engineer places 4 lithium battery packs into the metal box, wiring the power cables, and securely wrapping the battery terminals with electrical tape. The battery box is carefully covered and locked, ready to power the hub motor system. Drilling to secure the locking pins of the anti-vibration battery box lid. On the handlebars, the engineer uses a hex key to tighten the rearview mirrors, optimizing rear visibility. The electronic throttle assembly with an integrated battery display is slid onto the right side and locked in place with grub screws. The mechanical brake cables are meticulously routed and connected to the brackets of the wheel drum brakes to help slow down. Install the directional switch assembly to ensure flexible speed control. The dual cable brake system's tension is adjusted. The electronic heart is the central control unit, which is connected to the cables and motors. The engineer carefully inspects each signal connector, ensuring the 3-phase current is accurately distributed from the battery pack to the 2 rear drive motors. Powering up and twisting the throttle to test, the hub motors respond instantly, and the wheels spin smoothly. The finished product is a 4-wheeled off-road vehicle with a unique suspension and leaning steering mechanism. Its low-clearance design offers an optimally distributed center of gravity. The vehicle rolls out of the workshop and begins its real-world road test. Smooth acceleration, the electric motor operates quietly, and the suspension absorbs all shocks from the road. first-person perspective shows off its road gripping capabilities, with the tie rod steering mechanism providing highly precise feedback. The central pivot joint allows the vehicle's body to lean into corners just like a real motorcycle. The chassis demonstrates excellent stability during sharp turns, thanks to the double-wishbone suspension design, an impressive mechanical machine that serves as a testament to the perfect combination of mechanical engineering and modern electric drive technology.